So the first one was this integration. So I'm going to do integration, and I'm going to do ordinary differential equations, which are quite related topics, and both very important, but which have different applications. All right, so let me jog your memory about. Let's see, will this work? Okay. This is the integration sheet. So it says compute this integral. So we'll just go over the problems, and then we'll look at the code. So this integral is a regular polynomial. Should be straightforward integration by hand. And then estimate the integral using trapezoid method, which hopefully you saw way back in Calc 1. And then make a plot. So I've been trying to emphasize, well, it's not just about calculating the value. It's about seeing how your calculation method, how accurate your calculation method is. Every time you have a number, you should have an uncertainty associated with it. I mean, every time you compute a number in science, you should always have an uncertainty associated with it. So, and we've also seen that logarithms convey useful information. So often when you take the logarithm and plot the logarithm, you get a straight line. Because a lot of, if you have a polynomial relationship between two quantities, then that, I'm sorry, not a polynomial relationship, a power relationship between two quantities, then the plot of the logarithms is a straight line. We've seen that before. Let me put up my OneNote just so that you can see that. Okay, so we'll do that later. I'll add another one. So just say, so if I take a power relationship, like y equals a x to the b. If I take logarithms, okay, then I get log, and I don't care what base log it is. It could be natural log, it could be log base 10, it really doesn't matter. So it's equal to log of this, which is just equal to log a plus b log x. Right? So here you've got the slope here. So the slope of the log-log plot gives you the power. And that's a tremendous tool. The slope gives the power of the relationship. All right, so these kinds of graphs are very good tools to understand behavior of approximations. So we're going to do a couple of log-log plots, log of true error versus log of number of trapezoids, and then log of approximate error versus log of number of trapezoids. Now, one thing we've seen before is that if a good sanity check is, you need to make sure that your approximate error is always bigger than your true error. If not, well, it's not always, but usually. If it's not, then there's probably something wrong. It's not always bigger, but it's usually bigger. Okay. All right. So then you get the slopes. So you can see why now. I ask you to compute the slopes and explain this result in terms of the theory. Okay. Now I have some comments on coding, which I can pass over for now. Let's see. So all right. So that's number one. Number two is similar. So you see 1, 2, and 3. I mean, 1 and 2 are basically a copy-paste. Shouldn't be, I mean, there seem to be a lot of parts in this, but it really should just be a copy-paste, pretty much, because if you defined all your functions as functions, then you just have to drop in another function, and you use the same code. And then 3 does the same thing with Simpson's rule, and then 4 does Richardson extrapolation. So let me go on and do question 1. So question 1 is evaluate the integral, and here it is. Straightforward integral out of Calc 1. And then here's the true function. Of course, you need the two limits. And so the two limits are the argument of the function. and here is the actual integral that we need. Once you define the integral in a cell, you can use it in subsequent cells. So let me go ahead and do run all above, make sure I have everything. And I think we're good, and then I'll run this, and it should be fine. And let's go to part B. All right, so the way this is a very nice organization. Typically, you begin your code with imports, then function definitions. So here's the integrator. You need the integrator to do trapezoid rule. And then here's the trapezoid rule. If you remember, the trapezoid rule basically just sums up the value of the function, except for the 0 and the -1, which have a coefficient of 1/2. So this is a way to do it without loops. Of course, there are other ways to do it, but this is a nice way to do it. Very elegant. Remember, the -1 means that this is the last entry of the array. So we created an array of evenly spaced points. There's n plus 1 points. N plus 1 points means there are n intervals. So we've seen that before. If you just think, if you have 3 points, 3 points define 2 intervals, 4 points define 3 intervals, and so on. All right. So this does the trapezoid function in a very straightforward way. Then we define the limits of integration. Now you can define the constants before you define the functions. It really doesn't matter. But those are all things that you should set up at the beginning of your code. And then here you have your n values, right? So this is a nice way of generating the successive powers of 2. Right? That's kind of the broadcasting feature of NumPy. I create a range of 8 is 0, 1, 2, 3, up to 7, and then I can take 2 to the power of each one. So that will give me the first 8 powers of 2. That's a nice way to program it. All right. So then we need to store values. We need to create some space to store the values because we generate the values one by one. It's much better to do it this way than to use append. A lot of people just create a value and append it to a previous array or a previous list. It's a much better way. It's faster and it's neater. So I do recommend you do it this way. All right, so here we go, and this command here, enumerate, generates an index I, which goes 0, 1, 2, 3, 4, and also includes the values. All right, so if you see n values is going to be 0, 2, 4, 8, 16, and so on. So the first time through the loop, this will be 0. And this will be 1, because that's the first n value. Second time through the loop, this will be 1, and will be 2, because this is the second n value. Third time through the loop, this will be 2, the I will be 2, the n will be 4. So it's nice that it has both the index and the value in the array. So this is really nice. When I was growing up in programming, you didn't have this. And I think a lot of languages don't have this. So this is a really nice feature that Python has. So you need the index because you need the index to label the value of the integral that you're computing. Right? You're going to compute first the 0th entry of trap integrals, then the first entry, and so on. So that's why we have the index I here. The index I is telling me where do I put my result. And then you put the n here because that's the number of intervals you're using to compute the trapezoid function. Right? So this is very nice code, and we run it, and it should work. And if we look at this convergence, just by looking at it, well, let's see. You can't really tell at the beginning. Well, if you look at the difference, I mean, you can just look at these differences. When we plot it, you can see. So the difference between this and this is 3. Difference between this and this is 3/4. So it looks like that it's going down by a factor of 4 each time so far. All right, so this was 3/4. I don't know if this is 3/16, but you can see roughly here, this is 0.15, right? This is 0.0039, which is roughly 4, So this is roughly 1/4 of this. Then here we have 0.97. Multiply 0.97 by 4. Well, that's roughly going to take you, well, 9 times 4 is 9. So that's about, so 10 times 4 is 40. So this is about 4 times. So it looks like it's going down by a factor of 4 each time. And since it's a multiplicative factor of 4, when you take logarithms, that becomes an additive factor. And so let's see what we have here. So here's the plot. Plot is pretty straightforward. So here we have the true error, which is the true integral minus approximate integrals. Okay, and that's fine. We don't need to do a loop. This is the broadcasting of NumPy. Here we have the approximate errors. And so the approximate errors are going to be the difference between successive approximations. All right, so you can't. So this is what this does is that this takes all the approximate integrals, starting with this is actually the first index. The index 1 actually is the second value. So I'm taking values 2, 3, 4, 5. So something like this. If I grab this, you can see how this works. I think people may know this, but it doesn't help. It doesn't hurt to go over this again. If I take this expression here, and I will grab it and I'll put it here. So what does this actually say? Down here, right here. So, let's see. For instance, if I just had approx integrals. If I just get some values here, it says 1.1, 1.7, 1.9, something like that. So then that means that approx integrals of 1 colon well, that means I'm starting at the second entry. So that's going to be equal to 1.7, 1.9. Okay. Then if I take approximate integrals colon minus 1, doesn't this go down for me? It's not going down. Maybe I can do this. Oh, I can. Okay, good. So if I take approx integrals and I take colon minus 1, well, that's going to do everything except the last entry. So it's going to be 1.1, 1.7, right? Right. So if I take the difference between these two, if I take 1 colon minus approx integrals, I'm writing sloppy because I'm trying to write fast, colon minus 1. If I take the difference, you can see it's 1.7 minus 1.1, and then it's 1.9 minus 1.7. Okay. Since you're starting here with the first one, you're going to take the first one. You're starting here with the second one. You're going to take the second minus first, third minus second. Okay. So that's a nice way of getting successive differences. Now there is some Python function called diff, and if you have an internet connection, you can look that up. I generally have trouble remembering those things. This is a nice way to do it. You don't have to remember anything. Okay, but I think you can look that up. I think this np.diff will give you the difference series. You can do that too. All right. So then we have a plot. Here's a function to plot. Here we see again our old friend enumerate. So you have the index and the integral values. So you can get so here you do the true, let's see. So this is the true error, and then the approximate error. And actually, I'm not sure that you actually needed a loop here. Maybe you do. Oh, yes, you do, because you actually have several of these. You have an integral list for each. You have an integral list for each approximation. All right, so let's see how this works. Actually, I don't know if you did need a loop here. Do you really need a loop here? Let's see. Yeah, I'm trying to remember here. Let's see. Integral list. Integral list is just a. Well, is it a list of? Well, let's see what it is. I think you probably don't even need a list there. So trap integrals 1. Let's look and see what is trap integrals 1. Let me just add a cell below. All right, so this is it's a single list. So I think you actually should not need a loop there. You should be able to do that without a loop because it's a single. It's actually a single Python or NumPy array. You can see it's a NumPy array here. So I don't think you actually need a loop here. But I don't want to spend too much time on this. This could possibly be improved and made without a loop. So here we've got our error, and you've got the true error and the approximate error. So true to form, the approximate error is a little bit bigger. In fact, the approximate error, if we move the approximate error over by 1, it would almost be exactly on the true error. But not quite. All right, so we've certainly got straight lines. So the straight lines indicate a power relationship. This plot should really say log of error instead of error, and this should say log of number of trapezoids, right? Because you are taking logarithms. All right. Why don't I just do that quickly? Because it's so this would be log of error. I think it's log of error, isn't it? And then log of number of trapezoids. Yeah, it's log of and then log of number of trapezoids. So just to be clear. All right. So what is so it's clear that it's a straight line. So what is the slope? The question is, what is the slope telling you? What is the slope of this line telling you? Well, it's telling you, so you can see that the error is going down as the number of trapezoids. Now, in fact, the number of trapezoids is inversely proportional to the size of h. We've seen h before in Taylor series, and that's the quantity that's shrinking down to 0. So here we have a power relationship. This tells me that there's a power relationship between the error and the number of trapezoids. And it also tells me there's a power relationship between the error and h. Okay, so that's pretty much what this tells me. So let's see how you compute the slope. All right, now if you see the way the slope is computed here, I mentioned before that in this kind of situation, to compute the slope, it's best to take the last 2 points in your series. Because the error in the error is also decreasing relative to the error. So here we're taking the last 2 points in the series, the last 2 points of y, last 2 points of x, and you can see that you get very, very close to -2 for both of them. So that's telling me that this method is order 2. All right? So the error is proportional to n squared. All right? It should be n to the -2, really, because of course it's going to go down as n increases. So if the value of n is double, the true error is approximately quartered. So it's actually proportional to h squared, which is another way of saying it. All right. So here we do the same deal with this other function, and basically just go through the same stuff. There's nothing really new here. And it turns out that you see basically the same behavior. Don't worry about the stuff at the beginning. That's just kind of noise. But what matters is towards the end. You're still getting this slope of -2. So this shows that this -2 relationship is consistent basically no matter what function you have. There might be some glitches here and there, but eventually it's going to go to -2. All right, now do the same thing with Simpson's rule. All right. So again, this is a lot of copy-paste. The only thing you need to do is change your trapezoid function to Simpson's function. Right. So here, and it's really minimal change, basically just changing one line. So this is also a nice way of doing it. In Simpson's rule, the endpoints are different, and every other point is different. Right. So, and the coefficients alternate, so it's 1, 4, 2, what, 4? It's 1, 4, 2, 4, 2, 4, 2, 4, 2, and then the last one is a 1. And you do have to make sure that you have an even number of intervals. So this is a nice way to do it. This here is putting a coefficient of 4 on every other value of f, right? Because this is starting with the second component of f. It's going to up until the last, but not including the last one, and has a step of 2. This one is starting at the third component in the f series, going up to not the last one, but the second, but from the second last, but second to last is not included, and has a step of 2 as well. And then at the end there, if we want to pull that over, and then you add the last one here. So this is basically one line change. Everything else is pretty much the same, except here you have to start with 2 intervals instead of 1 interval. One interval doesn't wash with the Simpson rule. Right. Now, very interesting behavior here. Here you have, when you do this on the first function, you get perfect on the first trial. Right. And now what that means is that, so if you remember, the first function was a cubic function. So Simpson's rule can integrate cubic functions exactly. Which is really kind of interesting, because Simpson's rule, if you remember, Simpson's rule is derived based on a quadratic approximation. It turns out that the quadratic approximation will give you the integral of cubic functions exactly. Because we're not approximating the function, we're only approximating the integral. So this is telling you Simpson's rule is doing really good. You're getting a lot of extra accuracy. So that's what we have here. Now this does pose some challenges for plotting, because if your true error is 0, your approximate error is 0, and you try to plot logs of those, they don't plot. So I guess in that case you really shouldn't even plot them, because if you plot log of 0, you get minus infinity. So let's see if we go down to Simpson's rule. So, I mean, there's 0 error, so you really can't even plot it. All right, so this is the second one. The second one does not have 0 error, but because it was a higher order polynomial. So here, this plot is actually wrong. I mean, this is not those are supposed to be showing the true error. The true error is not 2, the true error is 0, so I can't really even show it. And then here's the trapezoid here, which we had before. So it's better just to do it for the second one. So the second one is here. So what do we get from this? What do we get from this? Take a look at this for a minute and see what you get from this. This is telling a lot of information. Well, the important information is the slope. We do have consistency. If you see that the orange and the blue is trapezoid, the red and the green are Simpsons. Right? And those are tracking like they should. The trapezoids are parallel, and the Simpsons are parallel. It's quite interesting that the trapezoid approximate error and the Simpson approximate error are the same. I'm not really sure why that is here. Or it looks like they're the same. They might not be the same exactly, but it looks like they're the same. But that's really not important. What's really important as far as numerical analysis is concerned are the slopes. And you can see the slope of Simpson's is considerably steeper than the slope of trapezoid. You go ahead and calculate the slope, you get minus, well, you get, for the second one, you get -4. Okay. So that's really good. That's really good. What that means is that if you double the number of intervals, your accuracy is going to go up by 16. So your error goes down by a factor of almost 20. So it's much faster convergence, and so Simpson's rule is far preferable to trapezoid rule. Right now we have Richardson extrapolation, and if you had probability in the fall, you should recognize this as a Gaussian distribution. And this integral from 0 to 5 is basically half of the Gaussian distribution, so it should integrate to approximately 0.5. It should be very, very close to 0.5. And first part was to use trapezoid rule to compute the first 5 trapezoid rules. So that's these values here. So this is just using trapezoid rule, and then later on, well, let's see. Or for the trapezoid rule to calculate these intervals. Okay, so you're actually going to be taking differences. All right, so let's see what we got here. Let's see what we got here. All right, so here again we have our n values. First, to get the first 5 Richardson approximations, you need the first 6 trapezoids. So here we would repeat finding the trapezoids. Here we use Richardson extrapolation and use the formula direct from the book. And here again, I don't think you actually need a loop here. I don't think you need a loop at all, because you're just, let's see if we can actually do this. Well, first of all, let's run it and see what happens. All right, now if you just look at this, you can see how quickly the thing is converging, like from here to here. I mean, it's just converging very, very quickly. The difference between here and here is like 0.000001, and then the difference between this one and this one is basically 2 orders of magnitude smaller. So it is really going down. It's really going down very, very quickly. Now, I was claiming that we don't actually need a loop here. Because we have the trapezoid values, and here k is 2. So I'm thinking that I'm going to do an alternative here. And I'll say RE2, just for Richardson extrapolation 2. We'll see if we get the same values here. So here you're iterating through I, and you're starting with 1. So I believe that you could just take trap integrals 3. And here, since you're starting with 1, that would be 1 colon. And then you're going to take plus. And then the k stays the same. So this term, actually, this is my mouse acting up. So you would still multiply by this. And then you still multiply by this. So that would be this times. And then this is going to be, so here we do the same thing here. It's going to be the same thing here because you're starting with 1 plus. And let me put this down on the next line so it will all fit. So it's going to be this one. Then minus, and then I believe this is just going to be colon -1. I think that will do the same thing without any loop. So, so this is some fancy. This is fancy. I suppose we could do. So here I'm going to be not fancy. I'm just going to say print. Well, all right. We'll be fancier. Display RE2, and we'll see if we get the same values. We'll see if it even runs. All right, so you see you do get the same value. So a loop is not necessary. You should ask yourself whenever you have a loop, do you really need it? In Romberg, you do need a loop to go through successive layers, but all right. Now this also probably is not the best way to do it. You could put these Richardson extracts in a list. It's true that the Richardson extracts don't all have the same level, but it would be neater to put these in a list instead of having Richardson extract 2, Richardson extract 3, Richardson extract 4. So I could do something like this. I could say Richardson extracts is equal to empty list, and then here I can say, you would just put it in, put it in. Then here we would say Richardson. So here I would say, let's see, then what would I do here? And I think. Well, let's see. How many do I want here? So I suppose I can say that this is. I want to. How many do I want? I want 4. I want 4 of these. All right. Now, somebody. Are you guys still with me? Anybody still there?
Yes.
Okay.
Yeah, we're here.
Okay, good. Sorry, I've been rattling on quite a bit. Sometimes I do that. All right. So we have this here. So how many do we have? 2, 3. And 4. So it'd probably be better to do this. This is times 3. Okay. So then here I could just say Richardson extracts 1. And then here this would be Richardson extracts 1 I, like that. And then here I do. And then here again you would not need this loop. You could just do this as a. You could just do this as a single. Where am I? Sorry, I skipped around. And then this would be minus here. And then this one would be Richardson extracts 2. So you could actually do this whole thing as a big loop, and over K. So this would be, so here we'd have this, and here I need Richardson extracts 2, like that. And then this would be Richardson extracts 2. And then this would be Richardson. So same thing here. Well, we might as well, since I started, we might as well finish it. So here we have this. And then here we have this. And then here we have this. And then this would be 3. Okay. And then this would be 3. Whoops. Where did this length come from? I'm not sure where these, well, see, that's the problem here. I need these lengths. All right, so this is going to take more time than I want to do, but you could convert this to a list and make this whole thing be one big loop, and then remove the loops here. It's going to take too much time to fix this. But usually when you write a code and you look back at it, you can find ways to do it better. So I wouldn't expect you to do that in this assignment, but just pointing out some techniques that you might want to use. Okay, so here we have, so to do Romberg, you just, so this is, so you start with a trapezoid, and then you apply Richardson extrapolation as many times as you have the levels. All right, and let's see if it runs. And whoops, that's kind of weird. That's certainly not the right answer. So I would have to debug this. Well, let's see what the function is. Oh, here, this is the wrong function. I should test it on this function here. Where's the function here? Do we have a function here? Oh, same integral as in 4. So it should be the same integral here. So let me grab the function from here. And where is it? Okay, here we go. I think I can just do this. We can see if that gives me a nice value here. So I'll do this one here. And we'll see if we get 0.5 again. And you can see how fast it executes. All right, so it's good. It's very close. It should be about. In fact, it's not exactly 0.5. It may be very close to this. Now, if you want to find out what it is, we just go to Wolfram Alpha. And you can say integral 0 to 5. And maybe I can just say of standard normal probability distribution. It may actually give me this. It may be able to recognize this. Okay. All right. So this was correct. Now it didn't give me the. It didn't actually give me the value. It just told me what the formula is. So maybe I can put this in here. It's not letting me copy it. So maybe it's. Let me see if I can do this. So what did he call it? So that's called the error function. ERF of 5 over square root of 2. Right, there it is. 0.499997133. Okay, so let's see what the Romberg gave us. Look at that. 499999713. You can't beat that. Okay, that is pretty good for a sixth order approximation. Okay, so any questions on that? I spent 40 minutes on this. I'm probably going to have to do differential equations in less detail. But that was fun. All right, so let's go to differential equations, and we can look at that. So some of this, you get some of the same issues here. All right, so here's simple differential equation. Solve with pencil and paper. I think we can go through this very quickly. So this is it's exponential. And use Euler method, compute with these plots here. All right, so here we have so in this one, the parameters were defined first and then the functions. That's fine too. Now, of course, this could be done better because we could just do two star and use a range. So that would be an easier way to do this. So we've got this. So we have the function, we have the derivative. The Euler method uses the derivative. Okay. So we have the steps. So each step is this divided by h, and then your let's see. I think dx and steps are the same thing. All right. But here you can see, like I said, I can't spend too much time on this. So this is, you can see the basic Euler formula here. The next value of y is the previous value of y plus the derivative evaluated at the x point. Oh, I see. This is this really shouldn't be dx. It should be the because these are the grid points and not the interval. So that name is a little bit misleading, but the math is right. Okay. So if we get the so here, so let's see. I'm not sure why we're excluding values where x is less than 0.5. Well, oh, that's right, because we did say that. Yes, that was part of the condition. So you should have done something like this, and you can see kind of this exponential behavior, and you can also see the convergence of these different Euler approximations to the exact value, which is the black one. But the convergence is not all that rapid. But this doesn't really show you much about the rate of convergence. The rate of convergence is shown when you take the logarithms. And again, what you want to look at is you want to look at the eventual behavior. You have straight lines that are parallel. And the spacing is more or less equal. The spacing between the first two is not so equal. But after the first two, you can see the spacing is more or less equal. So what is the constant slope telling you? The constant slope is telling you that there is a linear relationship between x and the logarithm of the error. Now notice this is not log of x, this is x. There's a linear relationship between x and the logarithm of the error. So that's a little bit different from what we had before. So what does that tell me about the dependence of the error on x? So we have the log of the error. Since it's a linear relationship, it's c plus, well, let's say d times x. Right? And we just take if we take the exponential of both sides, the error is equal to the exponential of c plus d times x, which is equal to x of c times x of dx. Now x of c is just another constant, so it's equal to k times e to the dx. All right? So the dependence of the error is exponential this time, not linear. So that means that means that these errors, the errors are actually the difference between these curves and the exact curve. And you can kind of eyeball it. If you took the difference between this blue curve and this black curve, it does seem to be increasing exponentially. So the error increases exponentially with x. Right. Now, this is actually a really profound observation. And it's quite general in differential equations, that your error increases exponentially. Now, what does that mean, that your error increases exponentially? Well, if you start with a very small, if you start with a very small error at the beginning, and that error increases exponentially, then eventually it's going to become enormous, no matter how small the initial error is. Because exponential functions become enormous very rapidly. So, for instance, suppose you have an error of 10 to the minus 6th here. Right? Now, at some point, you'll have that error will double. Suppose that error doubles after 1 unit of x. Now that wouldn't even be visible on this graph, that error doubling. You start with 10 to the minus 6. This is 2 times 10 to the minus 6. Right? So actually, I can plot this. I can plot this progress here. Suppose I have my error. Oops, sorry. And so suppose at the beginning it's 10 to the minus 6. Here it's 2 times 10 to the minus 6. And this is 1 second. Okay. Now, what that means is that the error doubles in 1 time unit. So this is going to be 4 times 10 to the minus 6. Okay. Then one more unit, 1 more second, is 8 times 10 to the minus 6. Okay. Now, suppose I go for 100 seconds. Or say, let's go for 60 seconds. How big is the error after 60 seconds? Well, this is, after 1 second it's 2 to the 1. After 2 seconds it's 2 to the 2. After 3 seconds it's 2 to the 3. After 60 seconds it's 2 to the 60th. Anybody know how big 2 to the 60th is? Well, 2 to the 60th is about 10 to the 20th power. So what's happened to your error? After 1 minute, this tiny error became enormous. So that's why we have disease. You get infected by just a handful of bacteria, and then within a while it becomes an enormous number of bacteria. There's also why you cannot predict the weather more than a couple weeks in advance, because weather is also governed by differential equations. You may have heard of the butterfly effect. So this has something to do with the butterfly effect. There's more to it than that, but this has something to do with that. All right. So, and that's a characteristic feature of differential equations, that small errors become enormous after a very short time, a surprisingly short time. All right, so that's what the slopes of these are showing. The spacing is showing that as h increases, basically as h increases logarithmically, the error also increases logarithmically. So that's actually showing the same type of dependence of error on h. It has a power relationship, just like integrals have a power relationship. And in fact, what you're doing here, when you solve this simple differential equation, you solve it by integration. So Euler's method is really a very simple integration method. That's really what it is. It's not trapezoid rule, but it's a simple type of integration method. So there's Euler. And then you can do this similar stuff for Runge-Kutta. Now, Runge-Kutta is much more accurate. And I'm running out of time, so I'm going to have to go through this very quickly. You can certainly see the difference with Runge-Kutta too. After 3 approximations, you can't even see the difference on this graph. But of course, if you go to the logarithm graph, you will see this. And you still have this linear relationship. You still have exponential error. And I believe that if you, I'm not really sure what happens, what the difference in slope here. I guess I didn't have you compute the slopes. I should have had you compute the slopes to compare the two slopes. But this is also showing, even with Runge-Kutta, the error is increasing exponentially. And I believe this spacing is larger between the different curves. What that means is that the order in h is bigger. And we represent that in another graph also. So Runge-Kutta 4, similar. You can't see the difference here in the log plot. You can see the spacing looks larger. So each doubling of h makes a bigger difference, and you still have this linear relationship. So even no matter how good your integration method is, you're always going to get this. You're always going to get this type of exponential increase in error. So now this is showing the error at the final time. So this curve, this looks very familiar. I think if you take you find these different slopes, you'll find out. I think so RK2. You'll find out RK2 is second order, RK4 is fourth order. So same type of information comes from these plots that we found for integration. Now, Euler's method for second order differential equation, basically instead of one component you have two. Instead of y and z, you could have done this as a single vector, and that's how you would do it if you have higher order differential equation. This is second order differential equation. Higher order would have more components here, and instead of writing it this way, you'd write it as a vector. But this gets the job done. And you can see this is the graph of a mass on a spring, like your car has springs. So when your car goes over a bump, the springs absorb the shock. If you have old shock absorbers, then they may bounce up and down for a while when they fatigue. So this is showing the bouncing up and down for a while. And if you want the technical term, this is called damped harmonic oscillator, and you might have seen that in physics. Now, in this damped harmonic oscillator, this is the mass that's on the spring. This is the damping. And so if I increase the damping, it will oscillate less. So we can just do that quickly. So if I increase the damping, like if I turn that to 2 minus 2.5, if we look at the function here, you can see it oscillating a little bit. This is called underdamped because it does oscillate more than once. And if you zoomed in on here, you'd see more oscillations. But if I run it again, let me just do run all above. It's taking a little while. Okay, so I'll run this one too, and we'll see how the graph changes. It should be less oscillatory. Well, it doesn't show much difference. Let's take it up to 4, and then we should certainly see difference. So I'm going to change this minus 2.5, I'll change it to minus 4. So we double the damping, and let's see what happens. Yeah, see here it just went straight down to 0, and it looks like it's bouncing up a little bit, but maybe not. If I increase the damping even more, you'll see that it just kind of goes down very gradually. If I change this to 8, and you can see that it will go down very gradually. So this means your shocks are your shocks are too stiff, and it's not. If you go through a bump, you would feel it very, very hard. I mean, what you want the shock absorber to do is go down rapidly, but not oscillate. If you change this to, if I make it small, if I make the damping small, you can see what happens. It was 2. So if I change this down to, well, let's look and see. If I put this to 0.5, we'll see what happens. All right. So there's your shock absorber going on for quite some time. But it should actually damp eventually. Minus 0.5 may be too small. Let's do minus 1. You should see it oscillating and damping at the same time. And there we go. Right, so that's your physics lesson for today. All right, good. So I want to introduce the next assignment. I just put it on or I'm about to put it on in the Google Drive under partial differential equations. So he did the theory for partial differential equations, and he writes out all the equations in gory detail. And here I just want to emphasize. I just want to do a couple of exercises to convert it into matrix form. Now this is not the right one. It's here. So as I said, I made this very nice long exercise, and I may do this. I may do this next semester in the finite elements class because that does solve partial differential equations. But I'm just going to ask you to rewrite the equations that he has in the text in matrix form, because I want to point out that these partial differential equations methods are really basically just matrix methods, and everything reduces to linear algebra. All right, so he writes Tij for his coefficients. So we're going to write it this way. The sub-index is the row index. The superscript is the column index. And let n be the number of nodes. So if you remember what T was the I think it, well, let's go back there. Let's see if I can just pull this up quickly. So I think I can look for a document, and it should have a PDE in it. Yes, it should be this one. So we're going to do parabolic. Oh, sorry, this is the PowerPoint. I want the text. It's this one here. So he should have this T here somewhere. Oh yeah, T was temperature. And temperature has two indices because it has both a space index, which is the subscript, and a time index, which is the superscript. So instead of writing subscripts and superscripts, we're going to put this in matrix form as Tij. N is the number of nodes. So that means the index I runs from 0 to n minus 1. And capital J is the number of time steps. Actually, this should be J to J minus 1. Sorry, if that's the number. Well, no, it should be capital J because that's the number of steps. You start at 0 and you take J steps, so it should be J. Okay. So this is actually going to be an n times J plus 1 matrix. Sorry. Right. So we let b of 0 be the value of Tij at the left boundary. And the left boundary means the first index is 0. And b of 1 is the value at the right boundary. Okay, so these will be your initial values. You can input this as a list or a NumPy array. So markdown is just, for the case n equals 6, then this is a column vector with 6 components. Right? Because for each j, then I can say for each j. Here we are. For each j, Tj is a column vector with 6 components. Oh, I already said that down there. Sorry. I should have looked ahead. Okay. But I don't really need a comment. Okay. Right, okay. And then I forgot to close the parentheses here. Okay. So I would like you to write, so 7, this 7 refers to the, in the text. Okay. So I'm referring to the text. Okay. So I want you to write 7 as a matrix equation of this form. And here I'm using Python notation again. That this means matrix multiplication. So if you remember, in the text, you have an equation for the t at time j plus 1 in terms of the values of t at time j. and you can write that as a matrix equation. And if you have 6 values of a space index, then it's going to be a 6 by 6 matrix. Okay. All right. So then, now, you can write it as a matrix equation. Then I want you to give a rule for the entries of this matrix M. Okay. You can write the entries of M, but you should be able to extract a rule. And the rule will have several parts. Right? In fact, most of the entries of M are 0. But you can find some patterns here. There's going to be one value when if k equals I, so those are the diagonal entries, and k is between 1 and 4. You're going to have another form if k equals I minus 1, and k is between 1 and 4. All right? So I want you to break down the entries of M in this fashion. If you look at M, you should be able to see patterns and extract them in this way. So there may be several additional conditions. You can see this only goes from k equals 1 to 4. You're also going to have to deal with k equals 0 and k equals 5. So those are the 2 diagonal entries in the corners. Right? So this is for 6, and then here you should generalize for arbitrary n. Now really, if you did this correctly, you'll just change the 4 to n, so, or to n minus 1. Okay? So from 2 to 3 should not be a big deal. And then write the matrix. Okay. So that will do it. I just want you to do parts 1, 2, 3, 4. All right. You don't have to. I think that will be enough. I don't want to overload you on the last week. But so there's going to be the first 3 are marked down, and the last one is a code cell. So you can put this all in a single Jupyter notebook. So we will not do 5 and following. We'll just do 1 through 4, and I'll make that very clear in the assignment. So do not, unless you're feeling masochistic, you don't have to go further on. But I feel kind of regretful because there's some nice stuff here. But it's certainly too much to do if we're going to finish everything by Friday. So I'll only ask you to do 1 through 4. All right, I'm 6 minutes over. Any questions? And I will post this recording. Hopefully I did it correctly this time. Anybody still there?
We're here.
Okay. All right, very good. Well, let me stop sharing. How come it's not stopping to share? I guess I have to go back here. I have to do this. And let me find where my Google Meet is. Here. Okay. Well, thank you for attending the class. It was fun. And we'll see some of you in the summer and some of you next semester. If you have questions about the summer, let me know. We still have, I think it doesn't start till the beginning of June. So you have a couple of weeks for breathing space. One thing that if you want to register for Dr. Roberts' course, you will get a hold. Don't freak out. It's just a glitch in the system. You can email me. I'll remove the hold. It's not a big deal. Okay, I will let you go. Have a good evening.
Have a good day. Thank you.
All right, thank you.
Thank you, Dr. Strong.
Melissa, we can. I'm going to close this and we can jump back on Google Meet after everybody's gone.
Sounds good, sir.
Okay. All right.
Thank you.
Okay, thank you. Okay, all right, bye-bye.